All right, so today we're going to look at a new topic called momentum and impulse. And my guess is you've probably heard about momentum before, but probably not impulse. So it's important they kind of go hand in hand. So go ahead and grab out your favorite set of physics notes and jot some of this down. All right, so first things first, let's just figure out what we know about momentum. So go ahead and take a look at questions 1, 2, and 3, and then answer them to the best of your ability. And then when you feel like you've got a good attempt on each of them, come on back and we'll go through them. Number one, it says list things you think have momentum. I remember when I was learning about this in high school, it seemed like my baseball coach always talked about momentum and you're swinging hard or whatever, and he'd actually use that term momentum. And then on ESPN, I remember this clear as day. You can see this picture down here of the outfielders, and they're going for a baseball. And I remember one of the outfielders, this guy named Jackson, crashed into this other guy who's flying off here named Johnny Damon. And I remember the ESPN commentators talked about how much momentum Jackson had as he flew into this other guy. And I thought that was interesting. Number two, why do you think these things have momentum? Well, my best guess, if you're watching this at home, is you're probably picturing something that's moving. And so things that are moving have momentum uh, is typically the answers I get. So in order to have momentum, you have to be moving. So Isaac Newton, back in the day when he was basically coming up with his theories of mechanics, came up with this concept of momentum. And let's go ahead and grab a pen color. Let's grab blue. So if we look at this equation here, Isaac Newton says, okay, the equation for momentum, in order for something to have momentum, it has to have two things. And the first thing it has to have is it has to have mass. So we talked about mass before with Newton's first law. If you have mass, Newton said you had inertia. And so now what Isaac Newton is doing, he's going even further and he's saying, okay, if you have mass, you have inertia, that means you want to keep doing what you're doing. But if your mass is moving, then you have this new stuff, and that new stuff is called momentum. So Isaac Newton says in order to have momentum, you have to have mass and you have to have velocity, which is a speed with a direction, right? And if you look at this equation, you might be kind of confused by it because m's for mass, you can see it's labeled mass right here, and then v is for velocity. And then notice that the letter for momentum is p. And at this point in the year, we're actually kind of running out of variables, so you're going to notice some of our variables don't really make sense. Like a lot of people might think that you'd use an m for momentum, but you can see in this equation here, you can't use an m for momentum because it's already used for mass. And that's one of the reasons I've heard it before. I'm sure there's probably other reasons why we use a p for momentum, but the symbol, the variable for momentum is p. And if you look, since mass is in kilograms and velocity is meters per second, when you multiply those two, your units from momentum are going to be kind of funky. They're going to be kilogram meters per second. And I always like to throw the algebra triangle on here if you have to solve for one of these variables real quick. So there that is. And then I also wanted to reemphasize momentum is a vector, and that's why I put that arrow above it. It matters which way your mass is moving, and it matters because your velocity in that equation is a vector. So momentum and velocity are both vectors, which means the direction matters. So that's a quick little introduction. A key concept with momentum is what's called the conservation of momentum. And I'm just going to go ahead and say, what is the conservation of momentum? And if you took chemistry last year, you probably talked about something called the conservation of mass when you're balancing your chemical equations. So maybe just take a second and see if you can figure out what conservation of momentum might be. All right, so conservation of momentum. Hopefully when you thought this through, you maybe thought back to chemistry and you thought conservation of mass. But for conservation of momentum, it says momentum cannot be created or destroyed. So you can't create or destroy momentum. Momentum can be transferred from one object to another. So basically, if some object has momentum, you can't just get rid of its momentum and poof, it's gone. Likewise, if you have momentum and you're moving along your mass, you can transfer that momentum to something else. And I put this picture of the baseball players back because, again, these guys were both running for the ball, and you could literally see this Jackson baseball player here was running, and then all of his momentum, his mass times velocity, when he hit this other baseball player, got transferred to that baseball player. And I think, if I remember right, this baseball player suffered a pretty bad concussion, but eventually was okay. So the big thing is momentum can be transferred. And Isaac Newton actually came up with this device right here. Take a second, see if you know what that's called. If you said Newton's cradle or Newton's spheres, that would be correct. And came up with Newton's cradle, which it says it right here. Nice job, Mr. Laurent. You put the answer right there. But basically, he wanted to illustrate this concept that momentum cannot be created or destroyed. And I just bolded it out here, but it says momentum before a collision is equal to momentum after a collision. So if you picture this, if you've ever seen one of these Newton's cradles, if you pull one sphere back and you pull it up to, like, say right here, and you let one go, how many is going to come out the other side? And the answer is one comes out the other side. If you pull two back, how many come out the other side is two. And believe it or not, this is a little confusing, a little tricky, but you can see there's 5 spheres here. If you pulled 3 spheres back, how many would come out the other side? And I feel like I shouldn't tell you the answer, but I'm going to tell you, if you pull 3 back, surprisingly, 3 come out. And I say surprising because notice you only have 5 spheres. So you pull 3 back, those 3 are going to collide with 2 spheres. So some people might say that 2 come out, but whatever momentum goes in, whether it's 1 sphere, 2 sphere, 3 spheres moving in, that's the momentum that has to come out. And I just put this little illustration here. So notice momentum in equals momentum out. And in real life, the Newton's cradle does not go forever because you have collisions with the air molecules transferring momentum to the air molecules. But my nice little illustration here, it just goes on and on forever. All right, so that's the conceptual definition of conservation of momentum. I want to take it one step further if maybe you're in honors physics class or AP physics class. So we're going to put the definition back up here, but we're going to take it into math land. In math land, it says a momentum before a collision is equal to momentum after a collision. So what I'm going to do is I'm just going to write that down as an equation. And it says momentum before equals momentum after. Okay, so conceptually that's my picture. Before momentum equals after. Another way you could say that is your initial momentum is equal to your final momentum. And instead of writing initial and final every time, I'm just going to go ahead and you can see I wrote PI equals PF. So whatever momentum you start with is what you finish with. And then all I'm going to do is I'm going to subtract PI over to the other side. So I subtract PI on this side and I do it over here. And that's going to give me this equation that says 0 is equal to PF minus PI. And some people out there might be like, well, why does that, what's the deal? Why would you have an equation where 0 equals PF minus PI? But this is actually a huge deal because if you take final minus initial, in physics class, we can use this symbol delta, the little triangle here, Greek letter, and that says if you take your final minus your initial momentum, it's equal to 0. And so this boxed purple equation is the conservation of momentum, but written as a mathematical equation. So it's saying for a perfectly closed system, your final momentum will always equal your initial. You won't gain or lose any momentum. There's no change in momentum. Now, if we go over to this Newton's cradle, the momentum in is not quite equal to the momentum out. So this ball goes in and this ball comes up, and then when this happens back and forth, this ball is not going to go quite as high and then not quite as high, and then eventually it's going to stop. So this is not a perfect system because it's actually losing momentum because it's having collision with the air molecules. All right, let's take a look here. Okay, there's other concepts we started with. We started with momentum, and then the second one up on the screen to start our video today was this word impulse. And this is the phrase that most people have not heard about before. So the question at the very top here, it says, how can you change an object's momentum? So let's say that you had a friend and you're playing a sport and they're running at you and you wanted to slow them down. Well, they had a lot of momentum. Well, how do you slow that person down and take some momentum away? Well, Newton says is that you have to exert a force for a given amount of time. So basically, if you want to change an object's momentum, you have to push on it with a force for a certain amount of time, and then he kind of comes up with a new vocabulary term. Isaac Newton says that if you have a force acting over a time, that's this new thing that he defines as impulse. And you're like, well, how does he come up with these terms? Well, he's doing calculus and all these mathematical kind of models of the universe. And he says this is a helpful thing. Like if you multiply an object's force times the time the force is acting, it's helpful to know that quantity. And then he called that impulse. And we just use an uppercase I. And some textbooks use different letters, but I believe ours uses an I. So impulse is equal to force times time. And if you want to change an object's momentum, you have to exert an impulse onto it. And as I'm recording this video, I have a glass of water sitting right next to me. and the glass of water is not moving. So I would say to myself, since it's not moving, it has mass but no velocity. So right now its momentum is 0. And if I want to give it momentum, if I want it to gain velocity so I can take a drink of it, I have to push on it or pull on it with my hand for a certain amount of time. So I can give things momentum by exerting a force over time. And a great example of this are crash tests for vehicle safety. So the Insurance Institute for Highway Safety, otherwise known as the IIHS, crash tests almost every car that you can buy. So I just looked at a Ford Explorer here because this one, I just saw the video on YouTube because I subscribed to the IIHS channel because it's kind of cool. But the Ford Explorer, we're going to take a peek. They're going to crash it at 40 miles per hour into a wall. And so, let's do an arrow here. So they're going to crash it into a wall. So it's going to have momentum. And as it crashes into the wall, you're going to see an impulse is acting on it, a force, and it's taking momentum away from that system. So let's go ahead and take a peek here. It's a brand new Ford Explorer. It actually gets a very good safety rating because it crashed it 6 different ways. We're only going to look at one of the ways, but you can see it really absorbs the force of impact very well. And I just want you to appreciate this car. Sorry, I didn't mean to do that. This car right here is going 40 miles per hour into basically a cement wall. So at 40 miles per hour, it has a huge mass because it's a very large SUV. It has a lot of momentum. So it had a lot of momentum, and as it crashes, a force is being exerted over a time. That's an impulse, and that impulse is basically changing the object's momentum to 0. Because when the crash is over, you can see it's at rest. Now, if there was no impulse there, then that car would have just kept going. So it kind of goes back to Newton's first law: an object in motion will stay in motion until acted upon by an outside force. It's just that now we're calling that an impulse. And you can see there's airbags in there because that extends out the time that the force acts. So that way the forces aren't so great on the people inside the car. And for most new cars, like the last 5 years, you can go onto their YouTube channel and you can check out your crash test of your vehicle, which is kind of neat to do. Yeah, let's come back here. All right, so that's an impulse, a force times a time. We're gonna finish with one more cool video. This is actually one of my favorite ones to show because, well, I can't spoil it. It says you have a 1959 Chevy versus a 2009 Chevy, momentum and impulse and action. It says in a head-on crash between 2 cars, in which car will the passenger be safer? And so 1959 Chevy, and then 50 years later, they make the 2009 Chevy, and they're going to crash them head on, and I believe it's 35 miles per hour in this one. And then they're going to have cameras all over the place and crash test dummies. And the question is, which passenger will be safer? So go ahead and think about this one. Hit pause first. Think about it for a minute or two. And why are you thinking about those things? Like, why do you think that car is safer? And then we'll come back. All right. So most common answers I get are split on this question. And you'd be like, well, probably from your perspective, you're asking, well, how could you possibly be split? Well, let's talk through the 59 Chevy first. There's going to be some car people out there that say they know that this is mostly steel. So this 1959 Chevy, most of the cars were made out of a lot of steel and metal back in the day. And they're going to say, well, Mr. Laurent, you just told us that things with a lot of mass have lots of momentum. And I'd be like, you're right. So they're going to say that you're going to be safer in the 59 Chevy. And then you're going to have the second half of class who are going to say, what? It's not the old car. All the newer things are always better. And a lot of times they'll say something like, it's been 50 years. You think Chevy would figure out how to make a safer car 50 years later. And then the other group will come back and say something like, well, they don't make stuff like it used to. So it kind of goes back and forth. But I do want you to think about one thing, is that they didn't crash test cars back in the day 50 years ago the same way they do now. So now you can go on and check your rating on your car, and if you have a horrible crash test, you're probably not going to buy that car. So I'll kind of give you a hint. It's going to be the 2009 Chevy that's going to be safer, and take a look why.